Welcome to the Deep Dive, where we help you navigate complex information fast.
Today we're tackling a really foundational piece of work in paleontology.
That's right, a paper that shifted how we think about life's history. Biological Extinction in Earth History by David M. Raup.
A classic. Raup really forced the scientific community to look at extinction differently.
Exactly. Our mission today is to unpack his investigation, looking at extinction not just as, the end of the line for some species, but as a major driver, maybe even a controlling force in evolution.
It's easy to think of it as just background noise, the constant turnover of life.
But Raup highlights the sheer scale. It's staggering, really. Virtually all species that have ever lived are gone.
Something like 4 billion species over the last 600 million years, the Phanerozoic.
4 billion gone. And that scale brings us to a core tension, a really big question we need to explore today.
Which is?
Is evolution mainly about Darwinian fitness? The best adapted surviving day-to-day competition? Or is it actually dominated by these huge catastrophic resets? External shocks, almost like a cosmic lottery, where survival is less about being fit and more about just, luck during a crisis.
Yes. That tension is absolutely central to Raup's argument and to understanding extinction's role.
So let's dive in. Where does the research typically focus when looking at extinction?
Well, while there's always some background extinction happening, the real action, the moments that reshape the biosphere, are these massive, relatively short events.
The big ones.
The Big Five, we call them. The 5 largest mass extinctions over the past 600 million years or so.
Okay, let's list them.
You've got the end Ordovician, the late Devonian, the end Permian.
Which was the largest, right?
By far the largest, usually.
Yeah.
Estimates for species loss go as high as 96%. It's almost unimaginable.
96%. Just try to picture that.
Then there's the end Triassic, and finally the end Cretaceous, or KT event.
The KT, that's one everyone knows. Because
Dinosaurs, of course. It happened about 65 million years ago.
But you're saying that dinosaurs are only part of the story.
A very small part, actually, in terms of the total biodiversity loss. Maybe only 20 or so dinosaur species coexisting right at the end.
So the KT is famous for the wrong reason, almost.
Well, its fame is deserved, but its real significance, evolutionarily speaking, is what happened next. It cleared the stage.
Allowing the rise of mammals.
Exactly. It facilitated that huge evolutionary radiation of mammals in the early tertiary. Without the KT event, well, we certainly wouldn't be here having this conversation.
So it wasn't just destruction, it was opportunity.
An ecological vacuum, yes. But the cost at the time was immense, particularly, as you mentioned, in the oceans.
What kind of numbers are we talking about there?
In the marine realm, estimates range from 60 to 75% of existing species wiped out.
And that includes common species.
Yes, crucially, it hit many abundant species hard, especially things like plankton. So if you think about it in terms of sheer biomass, the total weight of living stuff lost.
The mortality was probably even higher than those species percentages suggest.
Precisely. A truly profound biological crisis.
Okay, so that sets the stage. Now, let's get into that core scientific debate Raup waded into, this idea of continuous versus episodic extinction.
Right. The traditional view for a long time among geologists and paleontologists was that extinction was mostly a gradual, continuous process.
Sort of ticking along steadily in the background.
Yeah, often modeled mathematically as this steady, random decay. Van Valen's law is a famous example, suggesting a species' extinction probability is constant over time, regardless of how long it's already existed, like radioactive decay.
A neat, orderly picture.
A bit too neat, perhaps, because when Raup and others started looking closely at the data, particularly survivorship curves.
Like for those marine plankton you mentioned, the foraminifera.
Exactly. The pattern wasn't this smooth, gentle slope downwards. It looked very different.
How so?
It looked like a staircase, a step-like decay.
Meaning
You'd see these long, flat periods, the horizontal treads of the staircase where extinction rates were relatively low, representing stability.
Okay, background extinction may be happening there.
Perhaps. But then, these stable periods were punctuated by sharp, sudden drops, the vertical risers.
The mal-extinction.
Yes, sudden, high-intensity point events. This pattern strongly suggested the whole process wasn't continuous at all, but distinctly episodic. The big drops define the overall shape.
So the rare big events are what really matter for the overall picture.
That's the argument. Think of it like floods. You have average rainfall most days, maybe some drizzle that's background extinction. But the landscape is really shaped by the massive 100-year flood, the hurricane. Those rare high-intensity events overwhelm the long-term average. Mass extinctions are like those ecological hurricanes.
That makes sense. And this episodic view, it directly challenges the older ideas, doesn't it?
Completely. The old view favored gradual internal causes, things like slow sea level changes, climate shifts, and many thought searching for a single cause for any extinction was probably futile.
But if extinctions are sudden, global events,
Then you start looking for sudden global causes. And this is where things get really interesting, moving beyond just Earth systems.
you're talking about the Alvarez hypothesis.
Exactly. In 1980, Luis Alvarez, Walter Alvarez, Frank Asaro, and Helen Michel proposed that the KT extinction, the one that got the dinosaurs, was caused by the impact of a huge meteorite, maybe 10 kilometers across.
Which was controversial, to say the least.
Oh, incredibly controversial. Mainstream geology at the time really disliked catastrophic explanations, especially ones coming from outside the Earth system. But it sparked a huge amount of research.
And the reason it gained traction wasn't just the idea itself, it was the physical evidence they found, right, at the boundary layer.
Yes, that thin layer of clay separating Cretaceous rocks from tertiary rocks worldwide. It contains some crucial clues, empirical data points.
Okay, what were they? Let's break them down.
First, the famous iridium anomaly. Iridium is super rare in the Earth's crust because most of it sank to the core when the planet formed.
But it's more common in asteroids and meteorites.
Precisely. Finding a global spike of it right at the KT boundary strongly suggested an extraterrestrial delivery mechanism, a big one.
Like a calling card from space. What else?
Second, specific osmium isotope ratios found in that layer also pointed to an extraterrestrial source, matching meteorites rather than terrestrial rocks.
Okay, 2 points for impact.
Third, shocked quartz. These are quartz grains with microscopic structures that can only be formed under incredibly high, sudden pressure.
Pressure far beyond volcanic eruptions or normal geological processes.
Way beyond. The kind of pressures you get from a hypervelocity impact. That was a huge piece of evidence.
And the fourth?
Tiny glass spheres called spherules, which are interpreted as microtektites.
Molten rock droplets flung out by the impact.
That's the idea. Rock melted by the impact's heat and pressure, ejected high into the atmosphere, then raining back down globally as these tiny glass beads.
So iridium, osmium isotopes, shocked quartz, spherules taken together, that builds a pretty compelling case.
A very strong case for a sudden, catastrophic impact event coinciding exactly with the extinction.
But, okay, whether the cause is impact or something else, a key point Raup makes is that these major extinctions are selective. It's not just random death.
Absolutely not random. But, and this is crucial, the rules for survival seem to change dramatically between normal times and these crisis intervals.
How so?
While during background extinction, the slow trickle, things like having a large population size or a very wide geographic distribution usually protect a species. Makes sense, right? Harder to wipe out something that's everywhere.
Sure, seems logical.
But Raup showed this protection often breaks down during mass extinctions. For instance, he looked at mollusks across the KT boundary. Those with widespread geographic ranges had no better chance of surviving than those with restricted ranges.
So what made you fit for normal times didn't necessarily help when the catastrophe hit.
Exactly. It suggests the stresses were so different, so outside the norm, that previous adaptations became irrelevant or even detrimental.
Are there any general patterns to who survives and who doesn't?
It's complex and varies between events, but some tentative generalizations emerge. Large body size often seems to be a disadvantage, especially on land.
Like the dinosaurs.
Like the dinosaurs, yes. And perhaps surprisingly, tropical life forms often seem to suffer disproportionately more than those in higher latitudes. Maybe they're less tolerant of rapid environmental shifts.
Interesting. So analyzing the victims and survivors gives clues about the nature of the stress itself.
That's the key. Selectivity patterns are probably our best window into understanding the actual kill mechanism.
But drilling down to those patterns, or even confirming if an extinction was truly instantaneous, hinges on dating things precisely. And that seems to be a massive challenge.
It's arguably the biggest limitation in the field. The geological timescale is vast, and our ability to resolve events within it has limits.
You mentioned global compilations often lump things into stages like the Maastrichtian.
Right. The Maastrichtian is the final stage of the Cretaceous. It lasted about 8 million years. If your data resolution is 8 million years, You simply cannot tell the difference between an extinction event that took a week and one that unfolded over several million years. It all gets blurred together.
So you need finer resolution.
Hmm.
But even when you look locally at a specific rock sequence, there are problems defining the exact point of extinction. You mentioned the Lazarus effect.
Yes, the Lazarus effect. Named obviously after the biblical figure brought back from the dead,
So species disappear.
they seem to disappear at or below the boundary layer, leading you to count them as extinct. But then sometimes they reappear higher up in the rock layers, perfectly fine.
Meaning they never actually went extinct.
Exactly. They likely survived the crisis interval, perhaps in reduced numbers or in refuges where conditions for fossilization were poor for a while. So they temporarily vanished from the record, but not from existence.
So the Lazarus effect can make an extinction look artificially sharp or large at the boundary because you're counting survivors as victims initially.
Correct. And then you have the opposite problem, which complicates things further, the senior ellipse effect.
Okay, what's that?
This describes the fact that because fossilization is inherently spotty and rare, you're statistically very unlikely to ever find the fossil of the very last individual of a species right at the exact moment it went extinct.
The record will likely cut off earlier.
Almost certainly. So even if an extinction was truly instantaneous zap, everything gone at once, the fossil record will make it look gradual. The last known fossils of different species will trail off below the actual event horizon.
It smears the extinction backward in time.
Precisely. It truncates the species ranges downwards. This effect is why, for example, some researchers argue that finding the highest known dinosaur bone, say 3 meters below the KT iridium layer, doesn't mean dinosaurs died out before the impact.
It could just be the senior ellipse effect. We just haven't found one closer to the boundary yet.
Exactly. So you have the Lazarus effect potentially making extinctions look too sharp, and the senior ellipse effect making them look too gradual.
Which
Means interpreting the timing and duration of extinction events from the fossil record is incredibly tricky, and why even very capable researchers looking at the same data can sometimes reach opposite conclusions about causes.
wow, okay, so dealing with these limitations is key. Now, looking beyond single events like the KT, Raup and his colleague Jack Sepkoski introduced something even more radical, didn't they?
Ah, yes, periodicity.
The idea that these mass extinctions might not just be random episodic catastrophes, but might actually occur on some sort of regular cycle.
That was the bombshell finding from their statistical analysis of extinction data across different marine groups. They claimed to find evidence that major extinction events seem to be spaced roughly 26 to 32 million years apart through geologic time.
A 26 million year cycle of doom. That sounds extraordinary.
It was, and remains, highly debated. Proving statistical periodicity in a noisy geological record is very difficult. But if it is real,
If it's real, it almost forces you to look for an external pacemaker, something outside Earth operating on that timescale.
it pretty much requires it. You can't easily explain such a long, regular cycle with purely internal Earth processes. This led directly to various astrophysical hypotheses.
Like what?
Ideas involving the sun's oscillation through the galactic plane, or a hypothetical companion star to the sun, Nemesis, or periodic disturbances of the Oort cloud, that vast reservoir of comets way out beyond Pluto.
Disturbances that would send showers of comets towards the inner solar system.
Exactly, increasing the probability of a large impact on Earth roughly every 26 million years or so. So this periodicity concept, if true, provides a potential link between the impact hypothesis for specific events like the KT and a recurring underlying cause for mass extinctions in general.
Okay, so pulling this all together. Impact, selectivity, periodicity.
Yeah.
What does Raup's perspective ultimately mean for how we understand evolution itself? What's the question?
It forces a fundamental reevaluation. Is extinction primarily constructive, as Darwin might have seen it weeding out the less adapted, constantly improving life's fit to the environment?
Or is it mainly just perturbing?
Exactly. Raup leans towards perturbing, especially for mass extinctions. If these events are caused by stresses so extreme and rare, like the global winter and darkness after a giant impact, or massive volcanic outgassings, that they fall completely outside the normal operating conditions organisms are adapted to.
Then survival isn't about being better in a Darwinian sense.
It might just be about chance susceptibility. Did your particular physiology happen to tolerate prolonged cold? Could your eggs survive acid rain? Were you small enough to hide or hibernate? It becomes less about competition and more about weathering an unprecedented disaster.
The mammal-dinosaur example comes back here, doesn't it?
It's the perfect illustration. Mammals and dinosaurs coexisted for over 100 million years, with mammals mostly staying small and in the ecological shadows.
Then the dinosaurs vanish in the KT event.
And then mammals explode in diversity and size, filling those vacant ecological roles. But were the dinosaurs doing anything wrong evolutionarily right before the impact? Probably not. They were highly successful, well-adapted rulers of their world.
The KT event didn't select for better mammals. It just eliminated the competition.
It essentially cleared the board, allowing a previously suppressed group to radiate. Extinction here wasn't constructive pruning. It was a massive perturbation that reset the evolutionary game.
So where does this leave future research? What are the biggest outstanding questions?
For me, the most crucial area remains understanding the biological selectivity across different mass extinction events in much finer detail.
Really digging into the patterns of who lived and who died in each crisis?
Yes. Because comparing those patterns, the victims and survivors of the Permian versus the Cretaceous versus the Ordovician, for instance, is our best hope for identifying the specific environmental stresses at play in each case. Were they all impacts? Were some caused by massive volcanism, climate change, anoxia? The biological signature holds the clues.
So to synthesize all this, Raup's work fundamentally shifted the paradigm. It challenged that comforting view of slow, steady, internally driven extinction.
And replaced it with a picture where evolution is heavily influenced, perhaps even dominated, by sudden catastrophic crises, often driven by external forces.
Crises that are selective, but based on surviving the unusual event, not necessarily winning at the everyday game, and maybe even linked to cosmic cycles.
It paints a picture of Earth history that's less gradual climb, more punctuated equilibrium on a grand scale, long periods of stability shattered by these dramatic resets.
Which leaves us with a really provocative thought to end on, doesn't it? If these major resets are essentially down to chance survival against incredibly rare environmental stresses.
How much the grand tapestry of evolution that we see today is the result of organisms adapting and competing in normal times?
How much is simply the outcome of a series of cosmic coin flips, of pure luck, determining who happened to be standing when the lights went out?
It's a profound question about the balance between determinism and contingency in the history of life.
Indeed. Thank you for joining us for this deep dive into the history of biological extinction.